Thank you all for coming back, and for those of you that come for the first time, welcome to this CC-May Distinguished Seminar Series. And this series was started in 2015 in honor of Professor Cheng Mei for his contribution in fluid mechanics and mechanics. And we have the honor today to have Professor Cheng Mei with us here. And so for this closing talk of the term, and the goal of the series is to bring fantastic speakers from around the world. They're at the front of their domain to talk very broadly about the domain and get that propagated not only in CE but to MIT and the broader area. So I have a website written behind me, dss.mit.edu. There you can find the recordings of most of the talks that you can watch and reuse for teaching purposes or other educational purposes. And this series is made possible thanks to the support of the Civil and Environmental Engineering Department and the CC-May Fund. So we're grateful to that. So for today's speakers, we have the honor to host Professor Anne Karagozian. Dr. Karagozian is a distinguished professor in the Department of Mechanical and Aerospace Engineering at UCLA. Her research interests lie in fluid mechanics and combustion as applied to improved energy efficiency, reduced emissions, and advanced rocket propulsion systems. Professor Karagozian is a current member of the Air Force Scientific Advisory Board. She's a member of the National Academy of Engineers and a fellow of the American Institute of Aeronautics and Astronautics, the American Physical Society, the American Society of Mechanical Engineers. She received her bachelor in engineering from UCLA and her master's and PhD from Caltech in mechanical engineering. She's a member of the Board of Trustees of the Institute for Defense Analysis, IDA, and an alumna and a mentor for the IDA Defense Science Study Group. So without further ado, please join me in welcoming Professor Karagozian.
Thank you so much, Lydia. It is just such an honor and privilege for me to be here with you today, and I appreciate your attendance. Today, I'm going to be talking with you about the control of jets that are applied in energy and propulsion systems, specifically jets in crossflow. And the jet in crossflow is I hope you can hear me properly, is a flow field in which an injectant is typically injected perpendicularly into a crosswind. This has a variety of different engineering applications and propulsion systems in particular. This is a so-called canonical flow field, just as the free jet or the co-flowing jet is, or shear layers or wakes. This is a flow field that has complicated three-dimensional structures. It is thought to have improved mixing over that of the jet injected into quiescent surroundings or the free jet. This is a planar laser-induced fluorescence image of acetone seeded into a jet of nitrogen into crossflow of air. The momentum flux ratio of the jet fluid to the crossflow fluid is 12 in this image. The jet Reynolds number is about 1900. Just remember that parameter for just a second, jet to crossflow momentum flux ratio. The long-term goals of the research that we've been pursuing at UCLA for a number of years have been control of this flow field, what I call strategic control, not in a military sense, but rather using the properties of the fluid flow, the instabilities, to control in a logical, strategic manner for the various applications of the flow field. So among these applications are those in propulsion systems. So for example, jets injected into a crossflow are used for film cooling, for turbine blades, shown here. These small air jets, cooling air jets, are injected at a relatively low momentum flux ratio, less than 5, often less than 1, actually. There are other applications in engine systems. In air-breathing engines, for example, one injects primary air jets or so-called dilution air jets, again, to mix with products of the combustion process or react with fuel that's been injected and eventually cool the fluid upstream of the turbine blades. You can also use transverse injection of a diluent in a preburner section for a liquid rocket engine preburner. In these applications, the momentum flux ratio is relatively high, you would say, larger than 15, often larger than 30 or 50. But this kind of injection typically is used to enable cooling, temperature uniformity improvement, reduced fuel consumption overall for fuel efficiency. And there are also increasing evidence of the benefits of controlling the jet and or the crossflow to enhance mixing or cooling properties. And sort of, for those of you who are familiar with gas turbine engines and the pattern factor associated with the turbine, that actually can be reduced while the exit temperature is increased when you have this so-called strategic control. This is a sketch from my colleagues at UTRC. Actually, in other engineering applications that one would be pursuing, for example, in a civil or more importantly, environmental engineering department, there are also applications of the jet injected into crossflow, exhaust from steam electric or other kinds of power plants, effluent treatment plants. These tend to have a relatively high momentum flux ratio. That should have been the opposite orientation. And the design of the nozzle, the injection system, often can assist with that enhancement of mixing. Significantly, most transverse jet applications do involve a relatively high momentum flux ratio and also at the same time have the goal of enhanced mixing. And that, in a sense, is a little bit ironic based on the features that we have learned about this very interesting flow field. So let me tell you a little bit about the fundamental features of the jet and crossflow. The jet speed is uj, injected into a crossflow velocity, a bulk velocity of u infinity. There are a variety of vortical structures that are found to be present in this flow field when it is injected flush, as indicated here, with respect to an injection wall. There are shear layer vortices that typically arise especially at the upstream shear layer. There are horseshoe vortices that envelop the jet, wake vortices that are known to bring boundary layer fluid into the jet, and the very prevalent CVP or counter-rotating vortex pair, which is a dominant feature of this transverse jet. There are a variety of non-dimensional parameters used to characterize this flow field. The momentum flux ratio I defined earlier in terms of jet and crossflow densities and velocities, velocity ratio, density ratio, a Reynolds number we typically define in terms of the jet velocity and jet parameters, and Struhal numbers that characterize, I will particularly be characterizing Struhal numbers associated with the frequency of roll-up of the shear layer, of the upstream shear layer indicated here. And this can be scaled by diameter, it can be scaled by momentum thickness as well. And as I mentioned earlier, the jet and cross was thought to be an enhanced mixer even in and of itself as compared with the free jet. And it has been thought for many years that the CVP, this counter-rotating vortex pair structure, is one of the primary reasons for that enhanced mixing. And so I'll be elaborating on that in the course of my talk. In understanding the formation of that CVP, it has long been thought that this is associated with the roll-up of the upstream shear layer associated with the jet and crossflow. These are from experiments early on by Kelso et al. And indeed, when we performed 3D transient vortex element simulations of the jet and crossflow, if one were to integrate the vorticity field and take a look at the 3D structure of the jet when you see this vortex roll-up, indeed, you can recover a CVP structure. And I know Professor Gonim years ago was engaged in simulations of this sort as well. So when we began to study experimentally this flow field, now almost 20 years ago, remarkably, We began where we should have really ended, not ended, but we began a little bit further downstream than we really should have, in the sense that we were looking at gaseous jets injected perpendicularly into crossflow. The velocity ratio here is relatively low. This is smoke visualization of a nitrogen jet into a crossflow of air. So this is false color. And we began to actuate the jet fluid. I'll elaborate on that. But when we applied sinusoidal excitation using a relatively cheap Radio Shack speaker in the nozzle upstream of the nozzle, we would get some, vortical structure roll up, you could argue, but not much of a difference compared to the unforced jet. Whereas when we applied a controller, which was developed by my colleague at UCLA, Bob McCloskey, in collaboration with Luca Cortellesi, whom Lydia knows, when we put in a temporal square wave and periodically pulse the jet fluid, you actually can get deeply penetrating vortical structures periodically that form to spread the jet as well as increase the overall penetration, which overall people had thought had been associated with improved mixing. What's remarkable is between these two cases, this is an apples-apples comparison. We've matched the RMS of the velocity perturbation between these two cases, and yet one gives us remarkably different results. And by the way, for sinusoidal excitation, we had a very large perturbation in the velocity amplitude. This contrasted actually with the experiments done by some colleagues of ours at United Technologies Research Center who looked at a higher velocity ratio, and they did some planar imaging of an unforced jet and a sinusoidally forced jet in crossflow. That's what JICF stands for. And they only put in 30% of the mean jet velocity as a perturbation, but they were able to get remarkably improved spreading of the jet, improved penetration of the jet. And we did a number of experiments comparing square wave excitation, sine wave excitation. What we found in our studies, which were documented over in several papers, that square wave forcing at subharmonic frequencies associated with the fundamental shear layer roll-up frequency almost always improved penetration and spread of the jet, whereas sine wave forcing had a relatively minimal effect. And that was peculiar to us. That was confusing because our UTRC friends were able to get improvements, and we said, why? Why is there a difference? And we began then to study in earnest something that we probably should have started, but we didn't fully appreciate the fact that there would be this significant difference. No one had discovered this before. And that is, if you look at the jet in crossflow and say move a hot wire along the upstream shear layer, you will see different kinds of spectral characteristics of that shear layer representing the instabilities. So for example, if you have a free jet, you see a classic kind of spectral character here. The different colors represent different distances S along the upstream shear layer. Here the crossflow is turned off. You see the fundamental and eventually a subharmonic or a so-called preferred mode for the free jet. With a transverse jet, you see multiple modes, and they kind of interact and hop from one to another. As you increase the crossflow, U infinity, therefore reduce R. When you reduce R significantly simply by increasing the crossflow, you see very different spectral character. Pure tone instability, higher harmonics, relatively little evidence of a subharmonic as you do have for this velocity ratio. And then when you actually, and this is by the way for a flush nozzle with these flow conditions, when you actually take even better resolution of the hot wire measurements, this is a color map of much better resolution, greater resolution of the instabilities. So we're plotting here distance along the shear layer versus Struhal number. This is the typical sort of behavior you would see for a free jet. With a transverse jet, you get this sort of frequency shifting and hopping as you move along the shear layer, formation of a subharmonic, as is visible here. But when you achieve this condition, you have very strong pure tone instability, higher harmonics, no subharmonic. And this among a significant additional sets of results that we obtained, has told us that we actually have a transition in the shear layer from being convectively unstable to being absolutely unstable or globally unstable, where the instability actually takes over the entire flow field. And the character of the spectra are very different between the two. The ability to control is very different between the two. And in fact, let me just talk very briefly about what convective instability is in contrast to absolute instability, if you're not familiar. For shear flows in particular, convective instability in a shear flow is a dynamical amplifier. You put in a perturbation, and in space and in time, it will grow downstream, which is what happens for the transverse jet at relatively high momentum flux ratios or velocity ratios. When the flow is absolutely unstable, it is self-excited. It is like a dynamical oscillator. You put in a perturbation, and it grows downstream as well as upstream in time, taking over the entire flow field. There are many tests that one does traditionally to study that transition from convective to absolute instability, one of which very simply is to look here at the spectral character, but I'm actually here showing the time series data of the velocity perturbations as a function of time. And as we increase the crossflow, decreasing the velocity ratio R, very suddenly and abruptly, you get this very large amplitude increase. And that's one of the many pieces of evidence that tells you that you've transitioned to absolute instability. There are many, many more pieces of evidence that I will not show you today, including evidence of a Hopf bifurcation, if you are familiar with that. And these are documented not only for the equal density jet in crossflow in these papers. We also have stability analyses that have been performed that also show characteristics of this instability, but also for the low density jet in crossflow. The low density free jet is a flow field that is known also to become absolutely unstable with a low enough density ratio. And in our case, when it's below 0.4, or if the momentum flux ratio is below about 10, we do see that transition. So let me just show you one piece of evidence here, which is quite interesting. This is so-called Lockin, dynamical Lockin, where what's shown in black here is the natural spectrum associated with the momentum flux ratio 5 jet. When you apply external perturbations to the jet fluid using, again, a small speaker in the jet fluid, you get the spectral character that's shown here in red. This number is increasing, that suggests an increasing amplitude of the perturbation of the sine wave. So initially you might have, evidence of that other forcing frequency, which is different from the fundamental frequency. As you increase the amplitude of the forcing frequency, the evidence of the fundamental goes away. It actually eventually disappears, or we say it disappears. It's 3 orders of magnitude smaller than what it was previously. And we have defined that to be a so-called locked-in condition. And this is used very commonly in instabilities, wake instabilities, for example. And you can define that lock-in for a variety of different flow conditions, different forcing conditions, and you get what's called a lock-in diagram. So the flow here is locked in, the shear layer is locked into the forcing frequency. Otherwise, you're down like this. You might see evidence of the forcing, but the fundamental still hasn't disappeared. And you can look at this. This is for a density ratio of 0.55. You can look at this for a bunch of different momentum flux ratios as well. So you can define for yourself as you go from what's usually very strongly absolutely unstable toward convective instability, which is shown, or barely convectively unstable, a lock-in diagram, which tells you how hard you have to force a sine wave to be able to take over the shear layer. So this was of great interest to us. What was even better for us, because remarkably, as we began to publish some of this work on the transition from convective to absolute instability, here are our experiments here, there were a number of theoreticians who were skeptical of this. Have you looked at the evidence associated with a Hopf bifurcation? Well, yes, we did show that. Did you look at this? Did you look at that? And some were still skeptical until my friend and colleague Krishan Mahesh at University of Minnesota, who does direct numerical simulations of turbulent and transitional flows, actually did a simulation of our exact flow field in our experiment. Same shape of the nozzle, same inlet conditions, same inlet conditions for the crossflow. And remarkably, not only did he qualitatively capture, the strong pure tone, higher harmonic behavior, quantitatively, he got the same Struhal numbers as well. So it was really a remarkable verification of the same behavior we see. That little frequency shifting behavior, interestingly, arose because of our hot wire, because there's a tonal interference that's known to happen with a strengthening shear layer. So this gave us a lot of confidence about why it was now, and we began to understand why it was that when we tried to force our low velocity ratio jets in crossflow with a sine wave, we didn't get much of a response. It's because that flow was absolutely unstable. You needed to put in something much stronger, and that stronger kind of excitation that we put in was a square wave. And that sort of strategic square wave excitation was what was required to overcome and improve at least penetration and spread. But that's actually not the end of the story, and that's not the end of my talk. There is further tailoring that can be done to perhaps alter the dynamics of this jet and crossflow. But the biggest question is, we've been able to improve the penetration of the jet, the spread of the jet. Does that really mean improved mixing? And that is what actually gets me to the meat of the results that I'm going to be showing today. And the question is, do any of these results affect that CVP? Because the counter-rotating vortex pair has been thought for a long, long time to be associated with the improved mixing. Does it enhance mixing? And is the CVP associated with that? So here, finally, I'm showing you the experimental configuration that we more recently use. Here is our low-speed wind tunnel that we have at UCLA. We have optical access from the top, from the side, from downstream. Our jet injection system is attached to, again, we've used a bunch of different things, a very expensive modal shaker, for example, that's been used by my colleague for more detailed dynamical system control of the waveform, but also cheap $5 radio, used to be Radio Shack speakers, now we buy them from another vendor, actually work just as well in some circumstances. We've looked at several different jet geometries, injector geometries. A flush nozzle is one that actually forms a relatively thin shear layer, and that's one that has the most interesting dynamics. So most of the results I'll show for that, but we've also looked at a flush pipe, elevated nozzle where you actually inject outside of the crossflow boundary layer. We've looked at a range of momentum flux ratios, a range of density ratios. We've also looked at a few different Reynolds numbers. Mostly we've fixed the Reynolds number. And we look at largely nitrogen and helium that is injected into the jet fluid. However, in order to quantify mixing and to do more sophisticated resolution of the flow, we actually use a seeding with a fluorescent dye, acetone, that can be hit with a sheet of laser light that enables the fluorescence intensity to tell us about the concentration of the jet fluid. We also have done particle image velocimetry, and we use a dual cavity YAG laser as indicated here so that we can simultaneously, with 3 cameras, 1 for the PLIF, 2 for the stereo PIV, can capture simultaneously the scalar field, so the acetone concentration in the fluid, as well as the particles that are there, and hence the velocity field and the vorticity field. So here is just an example of what we get from PLIF imaging. For example, this is the scalar field of the jet fluid. You can see at this particular momentum flux ratio a roll-up of the shear layers, some merging that would be associated with the formation of the subharmonic in the upstream shear layer. Simultaneously, we can get from the PIV the vorticity field. So you can see the scalar location of roll-up corresponds very closely, or if not exactly, to the vorticity. And again, we use different species in the jet fluid, so that in fact with a mole fraction, say of acetone of 0.112, we actually need to adjust the mole fractions of helium and nitrogen to create the desired density ratio. So usually we use 1, but we also have looked at lower density fluids. We also take a look at the cross-section of the jet. So here's a PLIF image of the jet in cross-flow. If we take a slice, we can also image, as indicated here, the cross-section. So we can take a look, say, and see if we do recover the CVP, or counter-rotating vortex pair. In this case, we say that we do. It's kind of kidney-shaped, but largely you can see the cores of the vortical structures. We then were able to go systematically and take a look for the relatively high momentum flux ratio, moderate momentum flux ratio, low momentum flux ratio case at spectral characteristics. This is the same kind of color map I showed previously associated with spectra as you move the hot wire along the shear layer. Center plane images show roll-up of the vorticity pretty much where you begin to see the generation of the instability. As you increase the crossflow, that initiation of the instability moves closer and closer to the exit, as shown here. And this was not surprising to us. This is, again, the transition between a momentum flux ratio of 10 between absolute instability and convective instability. This was expected, not unexpected. This is what was unexpected. Where, low momentum flux ratio, definitely we saw a CVP, symmetric CVP structure. Pretty much at this moderate value of J we did as well. But at the larger values of the momentum flux ratio, we saw these very strange asymmetric structures with a tertiary vortex structure as well. And initially we were very, very skeptical of this. Just as, by the way, we were very skeptical of these differences in the shear layer stability characteristics. So my students tried everything to get rid of that. They assumed there was something wrong with the injection system. We have a 4-way injection system. They actually turned off 3 of the injection systems of the fluid into the jet nozzle to see if they could make it more or less asymmetric. It had no effect. There was nothing they could do to the jet fluid to affect that. There was a very tiny minor asymmetry in the crossflow, but even when they adjusted the tunnel, this didn't change very much. And very recently, actually, we were looking at some of this stuff again, and one of my students put in just a bolt upstream of the jet injection system to see what effect that had on the crossflow structure. It affected it a little bit, but it was still asymmetric like this. So this was quite bizarre to us. It actually occurs not only for the flush nozzle, which I just showed, but also the flush pipe. So here are the side views or center plane views for the 3 injection systems. As you become absolutely unstable, you have shear layer roll-up that occurs typically much closer to injection for the flush nozzle, not so much for the elevated nozzle. So that's where the interaction with the crossflow is very different. You don't have an actual boundary layer just upstream of what the jet is showing, and I can elaborate on that if anyone is interested. But what is most interesting is that at least for the flush pipe and flush nozzle, you have a very strange asymmetry that in fact depends a lot on the nature of that shear layer and potential asymmetries in the upstream shear layer. For the elevated nozzle, It's not completely symmetric, but it definitely is not a counter-rotating vortex pair as you have down here. So now we began to study a bunch of different things. What if you change the jet Reynolds number? But of course, what do you fix? There's certain parameters you can fix and then vary the others. In this case, we fixed momentum flux ratio, varied jet Reynolds number. And indeed, as you go to the higher Reynolds numbers, you see still an asymmetry, but it's not as bad as at the lower jet Reynolds number. Remarkably, others have seen this too. They have not elaborated on it, but I'll draw your attention to this case by Smith and Mungle, which actually was a little more than 20 years ago published. And my good friend Godfrey Mungle, who was at Stanford at the time, said, we tried everything to get rid of that asymmetry. It doesn't make sense. There's nothing asymmetric inherently in this flow field. Why should we see that asymmetry? In fact, it looks remarkably it's a much higher Reynolds number than what we've looked at. Higher velocity ratio as well, but it looks remarkably like this one here at our higher Reynolds number. So there is an inherent asymmetry that can be triggered, and this is something that was seen in more recent laser-induced fluorescence imaging by Shannon Dimitakis. Even simulations have shown some evidence of this asymmetry. So the question is, are these asymmetries, or is any of this relevant to the mixing? So now is where we began to look at actually how do you define molecular mixing and how do you employ it to study in this flow field. So for decades and decades, from the 1950s, 1960s, 1970s, people associated improved mixing for the transverse jet with an improved penetration. So I'll call this ZF parameter or ZP parameter penetration. You could look at the spread of the jet as well, either in the normal direction or the vertical direction as another measure of mixing. Those are so-called mean metrics. Those are the traditional metrics. Less traditional and slightly more recent is the concentration decay. If you have a measure of the concentration of the fluid, as this is from acetone plymph, as the concentration decays, you would say that you have an improved degree of mixing. So that decay also can be compared. But when we began to study this in earnest, we realized that one has to incorporate the transient effects as well as sort of the spatial variation. And what we have incorporated is one of many parameters that have been defined to quantify molecular mixing. And the one that we chose was the so-called unmixedness parameter. This is the second moment of the scalar field defined here. So what you do is within an area of interrogation, such as that shown here for the center plane view, or this cross-sectional view, you take a look at the local concentration, the mean concentration within the interrogation area, scale by the concentration at the injection, and in this case, when you scale with respect to the size of the interrogation area, you can come up with a number. And that number scales from 0 to 100%. And the lower the degree of unmixedness, the higher the molecular mixing. Others have used mix norm, for example, and we've used that parameter as well, where you actually vary the scale length. Here we have chosen unmixedness for a variety of reasons I can elaborate on later, but what's important to know is that we actually can vary our interrogation area to match the means values of the concentration among not only different slices of this jet that we take for comparison purposes, but actually among all of our flow conditions, so that when we compare the unmixedness for one case, it is comparable to the unmixedness scaled for another case. So this is what we use for our mixing quantification. And so I will not go into detail on all of these plots. All of them plot unmixedness in the ordinate as a function of either distance along the jet or distance downstream in some cases, I'll show. But in most of these cases, what you will see is as you move downstream, The cases where there is a lower unmixedness as compared to the cases up here at a given location means that you have a better mixer. And the better mixers almost always correspond to these lower J values where we found you have a symmetric cross-section, a CVP, and absolute instability. So transitioning to the absolute instability with cross-sectional symmetry, and I'm only showing you a very brief snapshot of the many, many cases we've quantified, seems to be the determiner for improved mixing. It's hard to make comparisons, but we do cross-sectional as well as center plane-based unmixedness, and they can become comparable when you scale the concentration in the same way. So when we actually have quantified these using this metric, the molecular mixing, we actually see that this transition to absolute instability is significant. You not only get a more symmetric structure of the jet, but you get an improved mixing of the jet. But you don't seem to get that when you have a higher momentum flux ratio. And remember, very early on in my talk, I said most of the engineering applications of the transverse jet are for higher momentum flux ratios above this transition to absolute instability. So is there a way to improve mixing for those cases? Can jet excitation actually improve this? And another question that I haven't yet answered is, what about this improved spread and penetration? Does that really mean better mixing? And so we began to go back to doing our excitation studies. We, again, have put in loudspeakers as well as modal shakers here with an actuation system that enables us to put in for sine wave excitation, we can put in a fairly clean sine wave. This is the temporal measure of the mean subtracted jet velocity at the exit plane measured by a hot wire. Can quantify the RMS of the velocity perturbation. Let's see what effect that has. Interestingly, not only did we get the lock-in behavior that I referred to earlier, but in the run-up to lock-in, before, this is at a given forcing frequency for the momentum flux ratio of 12 shown here. Black is the unforced spectral characteristic at a given location. Red is the forced. You get a lot of weird dynamical character. Not only do you see the fundamental, not only do you see the forcing frequency, which is down here, but you see linear combinations of these, of FF and F naught, the fundamental. This is evidence of what is called quasi-periodicity in the flow. So the dynamics have been studied in a lot of detail by my former student, Takeshi Shoji, where he even used a van der Pol model to study the dynamics, compared it with Poincare maps that can be extracted from these data. It's really quite remarkable. When it's locked in, though, you only see possibly a subharmonic and then higher harmonics of the forcing frequency. So we were able to generate a so-called lock-in diagram, once again, for different momentum flux ratios for this sinusoidal forcing. So interestingly, quasi-periodicity is something that was discovered here. When you're locked in, though, you tend to get a more robust roll-up of the upstream shear layer. And so I'd like to show you some examples here. This is for a momentum flux ratio of 41, clearly convectively unstable. Without any forcing at all, you have an asymmetric cross-section. When you put in a forcing frequency that is not locked in, that doesn't affect the cross-section. When you put in a forcing frequency and amplitude that is locked in, again, where the forcing frequency overcomes the fundamental, you actually can improve the symmetry quite a bit. If you continue to increase the frequency, if you're still locked in, you do get a symmetric cross-section. If you go beyond the range in our lock-in diagram where you're locked in, you really don't. There isn't much improvement at all. Even if you barely can get lock-in, as we've seen in some recent studies, you don't really see much of an improvement. So when you try to employ this lock-in phenomenon to the already symmetric cross-section for an absolutely unstable jet, it doesn't make a huge difference. But what we do observe is that indeed, when you take a look at unmixedness, for example, you do get an improvement in mixing when the jet is locked in and when you have, and that produces the best mixing. Interestingly, up here you have the so-called mean metrics, the traditional ones, jet penetration, jet vertical spread, and there's a discontinuity here just because of the thresholding used in the quantification of the spread. But basically, the best spread doesn't seem to produce the best mixing. So for decades, people thought, oh, improving the penetration, you're better mixed. But no, actually, if you look at the molecular mixing of the jet fluid, it's not necessarily true. We've done the same kinds of studies as you would expect for an absolutely unstable jet. You see almost no effect of this sinusoidal excitation. And then we began to go back to square wave excitation, which in our system with all of the additional equipment associated with the diagnostics became a little bit more difficult. But so what's shown by the dashed line is what we would love to have is a temporal square wave excitation. What's shown by the blue is what we would get out of our system without any control at all. It's not great, but it's definitely, there's no clear upsweep and downsweep. With the controller that is defined here using a feedback controller, Professor McCloskey and one of his students developed for us, where it is based on harmonics of the fundamental forcing frequency, we can actually capture a pretty decent square wave, except with a bit of ringing at the top, a bit of ringing down here. But what's important is you get a very clear upsweep and downsweep, and that's what produces a very nice square wave excitation for our jets. So for example, here is the J of 10 case. Unforced, it looks like this. With forcing, in some cases, and what this asterisk refers to as optimal penetration, you do get perfect periodic puffs of vorticity just as we did before. But beyond a certain range, you really don't have much of an effect. Now, L over D is a so-called stroke ratio. This is effectively the amount of fluid over time that is pulsed divided by the diameter of the jet. So it's basically a time times the velocity divided by the density, by the diameter of the jet. What is the effect of square wave forcing on the jet? Well, the unforced jet might look something like this. This is J of 10. As you increase the forcing amplitude for square wave forcing, increase the stroke ratio, you could actually get very different kinds of cross-sectional shapes, none of which really look like a clean CVP. But does that improve mixing? Actually, the cases where you have, let's look up here, the best penetration, which are shown by the asterisks, here's the penetration of the jet, here's the spread of the jet, do not correspond, generally speaking, to the best mixers. The best mixers tend to be these larger stroke ratios, where in fact what you're really doing, rather than putting in clean pulses of vorticity, you're really spreading out the jet a little bit better. And that intuitively would give you better mixing. So interestingly, there is this inconsistency, not inconsistency, but non-direct consistency between a well-penetrating jet and cross-flow and a well-mixed jet and cross-flow. And actually this was, let's see, is there a reason this is not advancing? Okay. This actually was something that was studied computationally by our friend at University of Minnesota, Krishnan Mahesh, where he studied pulse jets in crossflow as well and found that the optimal condition associated with this L over D, this stroke ratio, could vary with a velocity ratio and it would actually decrease. If you look at our data, so what's plotted here is L over D versus momentum flux ratio. The cases with the best penetration are open symbols here. And they indeed do tend to drop off with a reduction in momentum flux ratio or a velocity ratio. But the best mixing doesn't follow that trend. The best mixing actually seems to be optimized when you have this transition from convective to absolute instability. So we began to study many, many different cases. One was the idea of Luca Cortellesi. What happens, he said, when you put in two pulses, right? And again, the idea was you'd put in a short pulse, a long pulse, a high amplitude short temporal pulse, and see what that does, because in that case you might form one vortex and form another one right away. What happens if they collide, if they're forced to collide? Would that improve your mixing? And in fact, you can see that in this particular case, this is a fairly long short amplitude pulse, a higher amplitude short pulse. You form a vortex. The other one doesn't really collide with it very well, but a little bit. You can see after a while there is a collision of the vortical structures. This case actually isn't as good a mixer as this case is, where you form a vortex and another vortex grazes it. I don't know if you can tell, but it doesn't fully collide with it. It grazes it. And somehow that appears to enhance the mixing. So this is a flow field that we are studying much more extensively now. We're doing a bunch of different modifications now to our excitation system. One of my students who's about to defend her PhD thesis in a couple of weeks has put in some flush speakers. So here's the jet in crossflow. Here's the jet that comes out like this, the crossflow. And this is not exactly to scale, but you have 4 flush-mounted speakers that are embedded in the injection wall of our wind tunnel. And they can be operated sinusoidally such that they go 1, 2, 3, 4, or 1, 4, 3, 2. You can impose just outside of the jet either a clockwise perturbation or a counterclockwise perturbation, something like a helical excitation, to study the role of the helical modes, because there have been stability studies by Leo Alves and others that suggest that in some flow regimes, the helical modes can dominate over these axisymmetric instabilities. So interestingly, she did a Lockin study on this. And in fact, interestingly, when she achieved lock-in, here's the unforced jet at different downstream locations. So you see this clear asymmetry. This is, again, momentum flux ratio of 41. When she applies clockwise forcing, as I indicated on the prior slide, and if the flow is locked in, the shear layer is locked in, you do get some symmetrization of the jet. Same thing with counterclockwise excitation, but you get very different structures on occasion. And so we've done, my former student Leo Alves has done studies that suggest that the growth rates of helical excitation, +1, -1, are different. And this could be a manifestation of those inequalities. When you are not locked in, for either clockwise or counterclockwise excitation, you really don't see much of an effect. So the phenomenon of lock-in, or at least the run-up to lock-in, can have a profound effect on the jet. And these are just plots of unmixedness, once again, as a function of downstream distance for forcing frequencies below the fundamental, above the fundamental, but again with clockwise or counterclockwise excitation. I should note that the amplitude of the forcing here, by the way, is in fractions of a Pascal, as she quantified it using a microphone. In contrast, the excitation level that is required for our axisymmetric excitation to produce the results that I showed require on the order of 30 Pascals. So not large, but this is infinitesimal in comparison. So if you can really strategically force the jet in certain ways, you can improve mixing, improve symmetry, but it's not for every single condition. So it's important to understand the fundamentals behind this and why this occurs. Well, just one more aspect of the jet we've been studying recently involves placing a small tab in the upstream section, or at least or actually in different locations within the periphery of the jet. So here is the jet. This is not to scale, but a very small machined element has been placed on top of the jet exit to block a very small fraction of the jet fluid. The tab actually occupies about 4% of the whole cross-sectional area of the jet. Depending on where you place that, you can significantly change what happens to this jet in crossflow. So for example, when there's no tab, here are the same spectral diagrams I've shown before for a low momentum ratio, flux ratio, where you're absolutely unstable, higher value. When you place a tab right here at the upstream edge, that turns an absolutely unstable shear layer into one that's convectively unstable. It's very weak. You have significant delay of the roll-up of the vorticity, this tonal interference that we see typically with a higher momentum flux ratio jet. And it even further weakens the J of 41 case. Does this do anything for the jet in terms of cross-sectional alteration? Well, here is what happens to J of 5 up here, J of 41. When you place a tab upstream, let's just look at the 41, that's a little more interesting. That can make that weird asymmetric cross-section much more symmetric. It's not completely symmetric, but much more symmetric. Tab at 45 degrees, it actually can flip it around. So playing with that upstream shear layer and how that evolves is very significant. Even placing it downstream where you have wake vortices that can be important will alter that cross-sectional structure. And indeed, it also affects the nature of the mixing. Without a tab and at other locations, you have a better penetration of the jet with the tab upstream, lesser penetration. However, with a tab upstream, you get better mixing. Remember, lower momentum flux rate, lower unmixedness means better mixing. So we have a variety of different results for different flow conditions, and again, we're continuing to study this in our lab. So in conclusion, let me just tell you that the jet in crossflow really has a remarkable ability to produce substantial benefits in a variety of different engineering applications. But its control and optimization requires an understanding of the fundamentals. You need to understand the fundamentals of the shear layer instabilities. And then on top of that, the best ways to strategically control it. If the jet is convectively unstable, you need to apply a very different kind of control if you want to improve mixing than if the jet is absolutely unstable, where you would probably need some kind of much more carefully designed temporal waveform, such as a square wave or double pulse square wave. And square wave forcing can increase the penetration, but it may not improve the mixing. So in any event, we are looking at a variety of different kinds of excitation systems now. Our next step is actually to look at coaxial jets in crossflow, where we can actually actively change the nature of that upstream shear layer. So before I finish, let me just acknowledge my numerous collaborators, recent graduate students, early graduate students. Brett here worked in our lab, but on a different experiment, so I don't have your name here, but you know Sarah, who was in your graduating class. So in any event, I'm very happy that you were able to hear this talk, and I'd entertain any questions that you might have.
So when you compare this square wave signal with just sine wave, do you usually fix the amplitudes to be the same, or the mass, or the energy of the signal?
Yes, so the question is, what do you match between sine wave and square wave excitation to be able to compare them? we match the RMS of the velocity perturbation. So the root mean square of the velocity perturbation. So you need to actually know what the signal is for the actual sine wave or the actual square wave. That makes the most sense to us in the context of the transverse jet because when you measure an impulse, that is like the square of the velocity, and so that is what is captured by the RMS. Another parameter, though, that can be captured, not so much in comparing sine wave with square wave, but one square wave with another, is the peak-to-peak velocity perturbation, because with square wave excitation, you have a large upsweep and then a sharp downsweep. And very often that upsweep and downsweep amplitude is something that could be compared. You can scale that in velocity with respect to the mean jet velocity, for example. And that also has been used by our group and by others. Yes?
And for those asymmetric pictures, is there a circulation around the jet or not?
There is a circulation around the jet as it is injected by these horseshoe vortical structures that are known to form. There.
Is zero circulation around the rotating pair?
In our case, well, you have to capture all sources of vorticity in that slice. So let's see if I can go back to one of the examples, even maybe this one. So the vorticity would be matched among these, well, let's see. With the tab, you're reducing the mass flow slightly. So that might not be the best comparison to make. But the vorticity would be captured among as the same. You mean in comparison with cases where it's symmetric? Well, the trouble is the cross flow is different there. And so the nature of the shear layer roll-up is different. The nature of the initiation of the vorticity is different than in the shear layer. So the global vorticity would probably be different. On the other hand, this is actually a vortex structure. There is vorticity associated with this little piece of fluid. And there's others that, we may not be. This is a mean of 500 realizations, for example. So, yeah, indeed, it's going to be different, though, for different flow conditions. You couldn't really, you could compare it, perhaps, you could argue, at different downstream locations for the same flow field. But even there, let's see, I think I have the example from Andrea here. So, this is 2.5 diameters downstream, 5.5 diameters, 10.5 diameters downstream. But the jet orientation is like this. So we're looking at vertical slices because that's what you can do with planar laser-induced fluorescence. If we were able to take slices of that jet that would completely slice through the trajectory itself, trajectory-based slices, yeah, you would have a preservation of vorticity. But for this view, it would be approximate.
Okay, so Kelvin has emerged unscathed.
Kelvin has got to have emerged unscathed here, but there's vorticity in the boundary layer, right? There's vorticity in the wake vortices that are injected. So the sources, there are numerous sources of vorticity in this flow.
And did you look at the effect of the free stream turbulence?
Yeah, these.
Especially in the cases where you're looking at the penetration of the
Yes, we did vary the crossflow velocity for a pretty wide range. This is a Blasius boundary layer coming in, and in fact, we have determined you're not really even injecting the jet at a location near where Tolman-Schlichting waves might emerge. But these are all laminar boundary layers in the crossflow. Now, we did, I don't happen to have in this slide deck, but we did take measurements of the cross-flow velocity field at different locations. And as you get very close to the injection wall of the tunnel, there is a slight asymmetry that we detect in the velocity field, but it's not very large. And occasionally, if we alter things where it's the opposite in the asymmetry, it doesn't affect this cross-flow. There is something much more fundamental about it. And so I alluded to the fact that Leo Alves has done stability analysis. So he's done linear stability analysis, and he's engaged in global stability analysis for this flow, and has shown that for high momentum flux ratios, typically the dominant instability is m equals 0 in axisymmetric mode. But he found that there is an asymmetry in the growth rate between m equals +1 and m equals -1. Because there are natural asymmetries that can arise. And I think we're seeing evidence of that. I won't stake my life on it, but I think this is related to that anyway. Yes, Professor May.
In environmental fluid mechanics, Norman Brooks of Caltech many years ago did a lot of study on unforced jets and plumes in cross-flow.
Yes.
I just wonder whether you could comment whether plumes, there may be similar kind of interesting studies for forced plume, whether that can be a fundamental or application.
I think that would be a very interesting endeavor. Now, for a plume, you've got a significant density difference, and it would be more buoyancy driven. In our case, we have looked at jets in crossflow at a density ratio as low as maybe 0.3, 0.2. So jet fluid being a third the crossflow density. But still, the momentum flux ratios we're looking at are pretty high, so it's still momentum driven rather than buoyancy driven. But I would say absolutely you could come up with excitation methods, or even just design of the tower through which the effluent comes to maybe improve the mixing, because for sure, although on the other hand you might not be able to control the crossflow as well, but in fact having an adaptable control system could improve the mixing there, because you don't know what the wind is going to be like or the flow of the stream is going to be like.
With the asymmetry that you saw at the high J values, was it always in one orientation, or did you see it appear on both?
For this flush nozzle, let's see if I can go back pretty quickly. For the flush nozzle, it was always, at that momentum flux ratio, always in that same direction, which was remarkable. However, when we went to, let's see, okay, here. So this is a J of 41. This is the flush nozzle. This is the flush pipe, same diameter, same momentum flux ratio. It's flipped. A pipe has a much thicker shear layer, though. That has a paraboloidal velocity profile at the exit. Typically, you don't see, you see broadband instabilities, not really clean shear layer instabilities for a pipe as compared with a nozzle. But remarkably, this is quite repeatable as well. Notice the elevated nozzle. This is injected outside of the incoming boundary layer. So that is affected in a number of ways also, because crossflow comes in and then it rides up the side of the nozzle, so it actually weakens the shear layer. So you get kind of a blob, not really a vortical structure. But we have tried everything, and virtually always this is the shape you get. Now, if you increase the crossflow, but if the J value is still greater than about 10 or so, about 30 or 20, this flips in its orientation. So the dynamics of this flow are really fascinating. And I don't think we have, despite all the results that I've shown you, I don't think we've even touched all of the aspects and the surface of this problem.
If not, I have one. In one of the results that you showed with effect on mixing with the forced
Yes.
system, it looks like when you get it in the locked-in, that's when you're improving the mixing. But then there
Yes.
is a non-monotonic evolution with the frequency. So what's the relation with the frequency of, to the
Okay.
mixing?
Yeah, let me. Let's see if I can pull that up. Oh, here. Well, this is sinusoidal excitation that is axisymmetric. So yes, theoretically and in some applications, so a Lockin diagram of this, a Lockin diagram is something that is often generated for flows, especially that are already absolutely unstable. For wakes, this is done all the time. For low-density jets, for reactive jets, this is done. What is unusual about this is its asymmetry, right? That means that if you are 50% above the fundamental, you don't have to force as high an amplitude as you do when you're 50% below, or half of the fundamental. But what's even more interesting is J of 5, that's absolutely unstable. That's the sort of thing that people see also for the low-density free jet. But these are jets that are convectively unstable, and they kind of lie on top of one another. Typically, you would think that you would not have to force to any significant degree at all if the jet is convectively unstable. But as you get to the very low frequencies, you do. And it turns out this is consistent with stability analyses that show that for the transverse jet, you actually have growth rates that can be much lower and at lower frequencies, and hence you must force at a much higher amplitude to get any kind of effect. So we're seeing that here.
But in one of the other graphs, you had the actually unmixing
Oh, the
parameter.
unmixedness?
And that was when you, basically for the same J, but different forcing frequencies. Yeah, I
Was
think it was
this
this
it?
one.
Okay.
Yeah, that's right, this one.
Uh-huh.
So then the 2000 hertz is actually an outlier compared to the 14 and the 25 in the lower graph.
Yeah. Oh, and the lower one. Oh, you mean why is this one lower than this?
Yeah, so that suggests that.
Yeah. I don't fully understand this. These are fairly repeatable, although you could argue there are error bars in the quantification of unmixedness when you get to this low a level. The way we look at it is that it's a kind of group of frequencies that tend to produce better mixing. But interestingly, when you get to too high a frequency of forcing, so that's this dashed red line, this gives you a higher unmixedness, worse mixing. The jet, when it's forced at too high a frequency, just can't keep up with that excitation. A little bit like flames, but when it's natural frequency, here it's, for this particular case, I think it's around, here, it's 1600 to 1900 hertz. So when you're well above that range, the jet just cannot keep up with that kind of external excitation.
Any last questions? Not then, did you anything else?
Thank you.